Welcome to the deep dive. Today we're jumping into a really interesting set of sources you sent over, all about data compression. We're going to trace things from the very beginning right up to some cutting edge stuff.
Yeah, it's a fascinating journey. We'll touch on the history, some important names, and then really focus in on this new method called DualComp. It's all about how we make digital stuff smaller, faster, better.
So our plan is to follow that evolution, look at the problems people ran into, and then really dig into dual comp. We want to get into the more academic innovations, the really clever bits, and why they actually matter.
Right. And it does matter because, I mean, look around. Data is everywhere. Every photo, every message, every video stream. Compression makes it all manageable.
But it's always been tricky, hasn't it? Getting things super small, super fast, and making it work for, say, text and images. They're just fundamentally different beasts.
Exactly that balance. That's the holy grail, really.
Okay, so let's rewind a bit. The sources point back to 1948, Claude Shannon. Information theory. That's kind of the bedrock, isn't it?
Absolutely. Shannon gave us the math. He showed, there's a theoretical limit. You can only compress so much based on how predictable the data is. It set the stage.
And then came the actual algorithms, like Huffman coding in 52.
Yep, David Huffman, really elegant, still fundamental. Then Ziv and Lumpel in 67 with LZ77. That's the ancestor of things like zip, stuff we use constantly without even thinking about it.
Right. And then people started specializing, like PNG for images in 97 by Thomas Boutel, while general ones like BZIP2 and ZSTD also got better.
Yeah, but then the field took another turn toward, well, learning-based compression, using AI essentially.
So moving beyond just looking for repeating patterns.
Exactly. The idea was, what if we could predict the next bit of theta? Using neural networks, often language models. If you predict accurately, you only need to encode the surprise, the bit you got wrong.
And you combine that prediction with something like arithmetic coding to handle the surprise part efficiently.
Precisely. And that can lead to a much better compression, especially for complex things like natural language text.
But the sources say these early learning methods had issues, big ones.
They did. For one, most were built for just one thing, only text or only images, not both, very siloed.
Okay.
And then came the attempts with really big models, LLMs, large language models. They could predict well, sure, but the complexity was just
Which
huge.
meant they were slow.
Painfully slow. The sources mention things like LLMA 380B taking hours, maybe even days, just to decode a standard 1080p picture or a common text benchmark like INWIC 9.
Days. Wow. Okay, that's not practical at all.
Not even close. It's a major bottleneck. And there was this other attempt, Delatang and colleagues trying multimodal with LLMs.
And the sources weren't impressed.
No, because they basically treated images as if they were text. They ignored the whole 2D structure of images, the spatial stuff.
So they just flatten it out.
Pretty much. And despite having billions of parameters, it actually did worse on images than old school zip. It really showed you can't just throw a text model at images and expect it to work. You need something smarter.
Which I guess leads us directly to DualComp. The researchers position this as the answer, right?
Exactly. They call it the first unified and lightweight learning-based dual-modality lossless compressor. So unified image and text together. Lightweight, efficient.
And the goal was explicitly to handle that difference, that heterogeneity between image data and text data within one model.
Yes, to build something that understands both efficiently without the massive overhead or the pitfalls of ignoring modality differences.
And they picked a specific base model for efficiency reasons, RWKV7.
Right. The sources say their own tests showed RWKV gave a better trade-off between how well it compressed and how fast it ran, compared to other options like transformers or Mamba. Practicality was key.
Okay, so let's get into those core innovations. This is where the deeper academic stuff comes in, the clever structural changes they made.
Yeah, this is the heart of it. It's about how they design the model internally to manage both data types. Three main things stand out.
First up, modality-unified tokenization, so dealing with the input problem. Pixels are number 0 to 55, text is words, characters, totally different.
Yeah, how do you even feed that into the same system? Their answer is a shared vocabulary.
Shared. How?
Okay, so for images, they chop it into patches, scan it into a line, basically. Then each color value of each pixel, the R, G, or B, become a token. Simple vocabulary, just 256 possibilities.
Right, 0 to 255.
For text, they use a standard method, sentence piece BPE, which creates like 16,000 tokens for common characters and word fragments.
And they just merge them.
They merge them into one big vocabulary of about 16K tokens. But here's the really clever part, the academic bit you mentioned. It's about masking.
Masking.
Yeah. Before the final encoding step, arithmetic coding, the model predicts probabilities for the next token. If it's working on an image, they force the probability of all the text tokens to 0.
Oh, okay.
And if it's working on text, they zero out the probabilities for all the image pixel tokens.
Why is that so important?
Because arithmetic coding relies heavily on accurate probabilities. By masking out the irrelevant tokens, the model focuses all its attention on predicting probabilities just within the correct set of tokens for that data type. It sharpens the predictions, makes them more accurate, and boom, better compression tailored on the fly.
That is clever. Okay, innovation number 2, modality-switching contextual learning. This tackles the patterns, right? Text flows linearly. Images have this 2D spatial thing going on.
Exactly. Predicting the next pixel or word depends hugely on understanding the right context. And the context is just different. How do you make one model good at both?
So what's their solution?
They modify the core context mechanism of the RWKV model, the time mixing part, specifically the R, K, and V layers, which handle how much weight to give past information. Instead of one set of R, K, V, they create two sets.
Two set, yeah.
One set of R, K, V parameters trained specifically for text context, and another set trained specifically for image context.
And it switches between them.
Bingo. A simple switch directs the data flow to the text pathway or the image pathway for these specific layers.
Is that computationally expensive, adding double the layers?
That's the beauty of it. Not really, because R, K, V are just linear projections, relatively small, and you only use one set at a time during inference. So minimal extra cost at runtime, but as they say, notable gains because the model can learn fundamentally different ways to look at context for each modality.
While keeping other parts, like maybe the output layer, shared for efficiency.
Exactly. Targeted specialization where it matters most for context.
Okay, smart. And the third pillar, modality routing mixture of experts, MOE. Explain MOE again simply.
Sure, think of it like having a team of specialist doctors. You go to the front desk, the router, and it directs you to the best doctor, or maybe two doctors, for your specific problem. In AI, it's multiple small expert networks, and a router directs the input token to the most suitable expert.
And how does DualComp use this?
They replace the final big processing layer, the MLP, with this MOE structure. And critically, the router learns to send tokens to different experts based on whether it's an image token or a text token.
So image stuff goes to some experts, text stuff goes to others.
Basically, yeah. It adds another level of specialization later in the processing pipeline. It boosts the model's ability to handle both types of data by allowing different final processing pathways, increasing its flexibility and power without making the whole model massive.
And they kept this MOE part lightweight too.
Very. Only 3 experts in total, and they only activate the top 2 for each token. They tested different setups and found this gave a good performance bump for not much extra computation. They even showed diagrams where you can see image data uses the experts differently than text data.
So these three things, the unified tokenization with masking, the switching context layers, and the routing MO are the core structural innovations tackling that image-text difference.
Absolutely. It's a really thoughtful design.
And you mentioned that reparameterization training strategy before. How does that fit in again?
Right, that's another neat trick. During training only, they temporarily add even more pathways, like extra branches to those RKV layers. This helps the model learn better, find a better solution.
Like giving it training wheels.
Kind of, but then before they use the model for actual compression, they mathematically fold those extra branches back into the main ones. So the final model you use for inference, it's the original size, no extra runtime cost, but you keep the performance boost you got during training.
Train bigger, deploy leaner.
Exactly, a smart way to optimize.
Okay, so let's talk results. How does all this clever design actually perform? They use DITSPITE, lower is better.
Lower is better, yeah. And on images, DualComp, especially its image-only version, DualComp I, hits state-of-the-art or very close on standard tests like Kodak and CLAC.
And there was that standout result.
Oh yeah, the source highlights that DualComp I beats the previous best image compressor on the Kodak, set by around 9%. Which is great, but get this, it does it using only about 1.2% of the parameters the size of that previous model.
1.2%, that's tiny for a 9% gain.
Its incredible efficiency shows their architecture really works. DualComp itself also blows past classic PNG by almost 50%.
Wow. And text performance.
Also very strong. It significantly beats general compressors like Zip, that 57% game on NWIC 9 is mentioned right up front. And it holds its own or beats other specialized learned text compressors around the same size.
But the crucial part, maybe the killer feature compared to those giant LLMs, is the speed, right?
Absolutely vital. This is designed to be used. It hits near real-time speeds like 200 kilobytes per session, even on a regular desktop CPU.
Okay, that's actually usable.
Totally. And on a GPU, they benchmark it as being somewhere between 90 and 200 times faster than those LLM methods that took forever. It's not just faster, it's in a different league, practical versus purely academic.
And that efficiency carries through to the parameters too. It's not secretly two models bolted together.
Nope. Their analysis shows only about a third of the parameters are actually modality specific, like those split R, K, V layers or parts of the mode E. Most of the model is shared between image and text, much more efficient than maintaining two entirely separate systems.
So where do they go from here? Are they stopping at image and text?
Doesn't sound like it. The sources state clearly that the plan is to extend this, bring in audio, maybe video, work towards a more truly unified multimodal compressor.
The dream of one compressor for everything.
Getting closer, maybe. They also mention wanting to refine how parameters are allocated and improve the training further. Continuous improvement.
So summing it all up, DualComp seems like a really significant step. It shows you can make a single, light, fast compressor for very different data types like images and text.
Yeah, by being clever about the architecture, by designing it specifically to handle those differences with things like the masking, the context switching, the MoE routing, it avoids the pitfalls of earlier approaches.
It tackles that heterogeneity head on, rather than ignoring it or just using brute force with massive models. It's about smart design leading to both top performance and real-world speed.
Definitely. It's a compelling demonstration.
Which leaves us with a thought, maybe. If we have practical, fast ways to compress diverse data like this with one tool, how does that change things? Could a truly universal compressor reshape how we store, send, even process all this mixed data? What kinds of applications become possible when you remove that compression bottleneck for multimodal information?